Hello students, welcome back to another session. And as I said, I have splitted this second topic into few segments. And now we are going to start the heat transfer through structure. So this is the first segment in second topic. We will discuss the remaining content also. Here, so this is the second topic. So first we will see heat transfer through structure and then solar radiation, appliances, infiltration and ventilation. So we will discuss in subsequent sessions. And this is a very simple topic. We are going to see the heat transfer through structure and then we will move to solar radiation in next session. So the two main components of a cooling load during hot weather are sensible heat gain. So before starting heat transfer through structure, let me introduce the two loads. So cooling loads. So that is one is sensible heat gain. So sensible heat gain is nothing but when there is a direct addition of heat to the enclosed space, a gain in the sensible heat is said to occur. So when it is direct exposure, if sunlight is falling into room directly, so that is the direct exposure to heat, and a gain in the sensible heat is said to be said to occur. So this is nothing but sensible heat gain. This sensible heat is to be removed during the process of summer air conditioning. So air conditioning system should remove the heat that is directly entering into the space, confined space, or it can be a room. Sources of sensible heat gain can be the sensible heat gain may occur due to any one or all of the following sources of heat transfer. So one is the heat flowing into building by conduction. So heat flowing into building by conduction. So that is it occurs through exterior walls, floors, ceilings, doors and windows due to temperature difference on their two sides. So outside it will be more and inside it is less, and the heat transfer always takes place from higher temperature gradient to low temperature gradient. The heat received from solar radiation, it consists of the heat transmitted directly through glass of windows, ventilators or doors, and the heat absorbed by walls, roofs exposed to solar radiation and later transferred to the room by conduction. So conduction is the main culprit which transfers heat from outdoor to indoor. So conduction takes place through any of this medium, like it can be structure or it can be glass, it can be windows or it can be ventilator, whatever it may be. So through which the conduction takes place and it carries the heat from outdoor to indoor. The two main components. So next is the next factor. So the heat conducted through interior partition from rooms in the same building which are not conditioned. So even the one room is air conditioned and other room if it is not air conditioned, and definitely heat transfer takes place from that room to the air conditioned room. The heat gain off by lights, motors, machinery, cooking operations, industrial processes, etc. So these are all other ways where heat is produced and that is transferred to the confined space. The heat liberated by the occupants, even the persons who are sitting inside the air conditioned room, they also will exhibit heat. The heat carried by outside air which leaks in, so that is nothing but infiltrating air. So this is nothing but the heat carried by outside air which leaks in, so that is nothing but infiltration, and enters through the cracks in doors, windows and through their frequent openings. Even if we keep opening the door, that definitely there will be heat transfer from outdoor to indoor. And the heat gain through the walls of ducts carrying conditioned air through unconditioned space in the building. So even ducts which carries the air conditioned air, even that the ducts also will transfer heat through conduction from higher temperature grade higher temperature gradient to low temperature gradient, that is inside duct. The heat gain from the fan work, even fans, when fans are operated, there will be heat gain, and that should be that will be compensated, that will become load to air conditioning system, and that can be minimized or reduced. So next is latent heat gain. So latent heat gain, we have seen sensible heat gain, and this is a latent heat gain, and this is nothing but when there is an addition of water vapor to the air of enclosed space. So this is nothing but the water vapor is adding to the air. A gain in latent heat is said to occur. So latent, in the form of latent heat, the gain will occur. The latent heat is to be removed during the process of summer air conditioning. And sources of latent heat, so like sensible heat, we have the latent heat gain may occur due to any one or more of the following sources. And this is the heat gain due to moisture in the outside air entering by infiltration. So the heat gain due to moisture in the outside air entering by infiltration, and this is the heat gain due to condensation of moisture from occupants. Even condensation, that is in terms of sweat or some other way, the heat will be gained in the room. The heat gain due to condensation of moisture from any process such as cooking foods which take place within the conditioned space. So even when cooking is happening inside the confined space, there will be humidity, or we can say the latent heat will be liberated, and the heat gain due to moisture passing directly into the conditioned space through permeable walls or partitions from the outside or from adjoining regions where the water vapor pressure so is higher. So this is also one of the source for the latent heat, that is nothing but the heat gain due to moisture passing directly into the conditioned space through permeable walls. So permeable walls is like moisture walls, so moisture in the walls are partitions from the outside. Even in winter season, wooden doors also will exhibit this condition from the outside or from adjoining regions where the water vapor pressure is higher. When the outside air is introduced from ventilation purposes, so there is a sensible heat gain as well as latent heat gain. So both are possible. So the sensible heat gain is due to temperature difference between the fresh air and the air in space, and latent heat gain is due to difference of humidity only. So it is humidity plays a major role here in latent heat gain, and thus the total heat load to be removed by air conditioning and refrigeration equipment is the sum of sensible and latent heat loads as discussed above. So considering a building wall composed of a single homogeneous material, and heat enters the wall on the side exposed to higher temperature via radiation, convection and conduction. So all three modes of heat transfer is possible here when the wall is made with a single homogeneous material, and the heat flows through the material and disperses from the inner surface to the room side through similar mechanisms. Under steady state conditions, the heat transfer through the wall is expressed as, so Q equal to F naught T naught minus T1 into A plus K by X into T1 minus T2 into A plus Fi T2 minus Ti into A. So that is equal to UA T naught minus Ti. And this is the wall and the single homogeneous wall, and this is T naught and T1 T2 and Ti. So this is what happening here, and this is F naught and Fi. So where the F naught is outside film or surface conductance. So this is F is conductance, and Fi is the inside film or surface conductance. A is outside area of wall in terms of meter square. T naught is the outside air temperature, and T1 and T2 are temperatures at outer and inner wall surfaces in degree Celsius, and Ti is the inside air temperature. So that is Ti in degree Celsius. So this is the inside. So this is the inside and this is the outside, and this is the wall. This separates the both air conditioned room as well as outside environment. So X equal to thickness of the wall, and K is the thermal conductivity of the wall material, and this is U is the overall coefficient of heat transmission, and overall heat transfer coefficient is equal to U equal to 1 by F naught plus X by K plus 1 by Fi. So this is the formula to calculate overall heat transfer coefficient. So next is we have seen single wall, and when we have composite walls, so this is composite wall. It is made up of different materials, like it is also like concrete wall, and it is made up of one layer of concrete, that is cement, that is mortar, and there will be bricks inside, and there also it is a composite wall only, and heat transfer through composite wall. So here the you can see here temperature and conductivity. So let us have three layers, and when a wall is made up of layers of different materials, the overall coefficient of heat transmission is given by U 1 by F naught plus x1 by k1 plus x2 by k2 plus x3 by k3 plus 1 by Fi. So that is inverse minus 1. So where x1, x2, x3 is thickness of different layers, and k1 is thermal conductivities of respective layers, and walls with air space. Suppose if there is a space in between, so they like this. So there is a space here. This also will have different thermal conductivity, and when airspace is provided between materials, the expression for U is 1 by F naught plus x1 by k1 plus 1 by ka plus x2 by k2 plus up to 1 by Fi. So that is by minus 1 to the power minus 1, where ka equal to thermal conductance of airspace. So applications and considerations. So these type of multi-layered or insulated walls are used in cold storage applications, required low temperature insulation, so 10 centimeter thick. And for interior walls, for floors and ceilings, the adjacent room temperature is typically 5 to 10 degrees Celsius lower than the outside design temperature. And however, a special spaces like kitchens, boiler rooms, attics, and show windows, the inside may be hotter than outside outdoors. And practical engineering implications. Now you can see engineers must select wall construction based on thermal resistance and desired insulation effectively, and using air gaps, insulation layers, and surface finishes affect the overall U value significantly. So lower U values imply better insulation performance and reducing cooling load. So lower U value is always preferable and desirable, and if we have lower U values, it implies that better insulation performance and reducing cooling load. So I will show you different tables what is happening in the confined space, and this is a structure. So for structures with wind velocity of 24 kilometers per hour outside, so in with this, so U values are like this. And brick wall, it is 20 centimeter bare, so that is 2.84. This is the highest here. And this is 3.18, so that is the concrete blocks 20 centimeter bare. So a brick wall 20 centimeter plaster on side on brick, and a brick wall 20 centimeter plaster on one side on metal lath furt, and brick wall 40 centimeter bare. So we have different scenarios of brick walls. So cinder blocks also considered here. Cinder blocks 20 centimeter plaster one side and metal lath forward. So there is a coating, metal coating on the other side, and concrete blocks 20 centimeter bare, and clapboard frame construction, plaster on wood lath, and wood single frame construction, plaster on wood lath, and stucco frame construction, plaster on wood lath, and brick veneer frame construction, plaster on wood lath. So these are all the different structures we can have in practice. And in India we will be having most of the places brick walls, and plaster on both sides, or in few cases plaster on one side. So thermal conductivity K of building materials. So brick low density. So thermal conductivity is 8.66, and thermal conductivity is very high in the case of these places. That is cement mortar, and cement plaster, concrete typical, and sand and gravel. So in all these cases, the thermal conductivity. So here you can find this in the refrigeration and air conditioning tables also. But you can see the different materials, how they are producing the thermal conductivity, how the thermal conductivity is impacting the air conditioning system for different materials. Next table, for insulating materials. So we have thermal conductivity for insulating materials also. So there is no material which is the perfectly thermal insulator. So there is no thermal insulators. Every material will cause thermal conductivity. So asbestos packed, it is 2.812, asbestos loose, and asbestos paper, and asbestos mill board, and asbestos wool, and alfat roof. So there is felch and balsa, cement wood, and charcoal, caulk board, and caulk regulated coarse, and cotton. Even cotton is a very good insulator, in thermal insulator. And diatomaceous earth, and eel grass wool, hair felch insulation board, with made up of, are composed of different fibers, and nyack, and this is nothing but wood panel, planer shavings, rock wool, rubber, sawdust, various from various woods. So all possesses a very good thermal very good insulators. So thermal conductivity is very less. In the asbestos wool, it is little higher, but almost all the materials causes lesser than single digit, that is unity, say lesser than unity thermal conductivity. Next, we have conductance of building materials and construction for a given thickness. So here, these are all the materials: plaster board. So that is the conductance here. So these are all conducting very higher, very the thermal conductivity is very high in shingles. So that is slate, and this is 58.96. And whereas sheathing 25 plus paper, it is very lesser, it is 4.65. So even materials having the thermal conductivity in a very high range. So film or surface conductance for air films and air spaces, and this is the still air, and when it is in horizontal, the thermal conductance is 9.25, and the still air heat flow and the sloping 45 degrees it possesses 9.1, and still air heat flow, and the heat flow is from upside down, and this is horizontal, and 8.3 still air heat flow reduces, actually here also heat flow reduces, sloping 45 degrees, that is 7.5 conductance, and wind at 24 kilometers per hour any position it possesses 34 thermal conductance, and whereas wind at a half speed, that is 12 kilometers per hour, it possesses 22.7 thermal conductance. So airspaces bounded by structural materials. So here heating flow up, so that is horizontal, it is having 6.7 heating flow up, so that is sloping, and heat flow horizontal, vertical, and heat flow down, that is sloping 45 degrees, heat flow down, heat flowing down, and at a different surface thickness, so that is horizontal 19 millimeters, and horizontal 38 millimeters, horizontal 100 millimeters. So these are all the thermal conductance varying. So it is for horizontal heating flow up, it is 6.7, and coming down, it is horizontal for 100 millimeters thickness, it becomes like a insulator. And you can refer these books, and you can refer CP Aurora, or we can refer as usual RS Kurmi. RS Kurmi is a very good book. I have taken this particular topic from RS Kurmi. Please refer, and I will also post this material in Google Classroom. So please prepare well from this material. And we stop here. In next session we will start solar radiation, and the solar radiation and its impact on air conditioned space. Thank you, students. We stop here, and we will start the solar radiation in next session.